Class, this is a tutorial on recursion. This is assuming that you've already watched my lecture on Building Java Programs, Chapter 12 on recursion. I'll put a link to it up here. And that will give you the basics, and you should definitely try some practice it problems, such as ways to climb, and take a very good look in the book over how to do traveling northeast. But assuming you've done that and you're getting ready for a quiz, I want you to lead you through a number of examples here. I'm going to give you three simple recursion examples, and then three recursion examples with recursive backtracking. So the first one is going to be a simple iterative like recursion. It doesn't do anything fancy. You could easily do it with an iterative solution. In this case, I'm going to be doing a little bit different though, because many times I've shown you, oh, it takes n, and you recurse by giving it n minus 1 or something very simple like that. This is a little bit different. I'm going to recurse by n divided by 10. And this problem is going to calculate the sum of digits. So 1,234. And we want to calculate the sum of the digits. So 1 plus 2 plus 3 plus 4 is going to equal 10. So we've got this simple recursion function. We don't need a helper function for it. Whenever you do recursion, by the way, as I go through these problems, I'm going to be showing you the code, but I want you to stop the video after I present the problem and try to come up with your own pseudocode for the problem. I'll go over the pseudocode, and then I want you to stop again and try to go over the actual code yourself and try to get it working, and then I will show you the code. If you don't stop and do those steps, I can almost guarantee you're not really going to learn. The brain just doesn't work that way. You need to actually figure it out on your own and see what you don't understand. Otherwise, I can guarantee you from many of my students that I've caught cheating. The reason I catch them cheating is because they don't learn, and I realize they don't learn, and I look at what's going on, and it's almost in every instance it's because they've been cheating. They've been copying code from somewhere else. That does not teach you to learn. All right, sorry. Rant off. Let's go on. So digit sum, and so what is the pseudocode for this going to be? Hopefully you've already tried this. So the pseudocode, we've always got two different cases we want to list for recursion. First case is what is the base case. Second is what is the recursive case. Sometimes we have multiple base, sometimes we have multiple recursive. And these simple ones we don't. So what is the base case for digit sum? So we want to make this problem as simple as possible. And you know from the very simplest examples that you go n and you take n minus 1, and eventually you get to 0 or empty or null string or something. And that's the base case. So in this case, we are actually going to be dividing by 10. So we're going to start by looking at 1, 2, 3, 4, and then we're going to drop the 4. So we're going to look at 1, 2, 3, and then we're going to drop the 3. So we'll just look at 1, 2, 12, and then we'll drop the 2, and then we'll just look at 1. And eventually we get rid of the 1, and so we're left with 0. So the base case should be when you get to 0. And when you get to 0, what is the sum of 0? It's 0, obviously. So what's the recursive case? As I showed you, the real key to the recursion, to figuring out how to code a recursive problem, not to figuring out how to write it one, but create one, but how to, when you're in a classroom situation and you're trying to figure out the recursion, you really need to understand what does it look like from one iteration to another. So I just showed you, right? It goes from 1, 2, 3, 4. We drop the 4. So now it's just 1, 2, 3. And then we drop 3. How do you do that? That is the question. If you can figure that out, that is your recursive statement. So hopefully by looking at this and through the class, you've realized that you can drop off the last digit of a decimal number by dividing by 10. So all we have to do is we take n, and we divide it by 10, and we call digit sum with that on it again. So we're going to and we do need to return that value because this function does return something. So we have to return the recursive call. We have to add the value of the ones digit. So we're going to knock this 4 off. We're going to return 4 plus, then we're going to recurse with 1, 2, 3. So I said digit sum of n shifted 1 digit right. And we just talked about how we're going to do that. So I definitely want you to try to write that code on your own. But here's the code. It's pretty simple. So if n is equal to 0, we're going to return 0. Recursive case. Again, so we're going to take the value of the ones digit, that's n mod 10, and then we're going to add on the call of digit sum of n divided by 10. So I'm going to be testing it on 3 cases. First, you want to make sure you test it on the base case, which you expect 0. I'm also going to test it on the case where there's a single digit, because that oftentimes is a place where you can go wrong, and then something with multiple digits. So when we run this now, 0, sum of the digits, digit sum 0 is 0, sum of the 5 is simply 5, and then the 1, 2, 4, 3 is 10. So that all worked correctly. So this is pretty typical of simple recursion problems where you have, again, you have an n, maybe it's going to decrease by n minus 1, or taking off a character. In this case, we're dividing the number by 10 in order to lose a digit each time. You're oftentimes going to have to, if it's going to return something, you're going to have to obviously return a recursion and then also modify it. Maybe you need to concatenate a string, maybe you need to add a value, maybe you need to add an item to an array list or something like that. And base cases are generally simple, but you can very frequently have multiple base cases where maybe if n is 0, it means one thing. If it's 1, it means another, or maybe 0 and 1. So n less than 1, it would return 0. So things like that, you need to make sure you handle all of your base cases. Okay, so let's take a look at another problem now. This one is another fairly straightforward, simple recursion. This time I'm going to be using strings. And this time I'm going to take a substring at each step, but it's not just going to be one character less. It's actually going to be, we're taking off the first and the last character. So the goal of this is to reverse a string, which if you write it iteratively, you're going to walk down the string. You're going to have to take a temp variable to store the character, and then move the last one to the first one, and then put that temp into the last one. We don't need temp characters because we're going to use the stack in recursion to be our temp character. So let's take a look at what it has to do. So you've got a string like hello, and we want to reverse it. So what you do in recursion is that you're going to take the first character, the H, and the last character, the O, and you're going to swap them. And then you're going to recurse on the middle. So then you're going to take the last character, which is the E, and then so the first character would be E, the last character would be L, and you'll swap those. And then you're just down to L. And we define that L is already reversed. We don't have to do anything. How about an even length string? You've got to make sure you pay attention to even and odd lengths. So if it's an even length string, you're going to swap the J and the N. Then you're going to come in, you're going to swap the O and the H, and then you're going to be left with nothing, the empty string. And we define that as well is already reversed. You don't have to do anything. So what is the base case and what is the recursive case, as always? So the base case is if you have success, and success means that we've reversed everything and we're down to either nothing in the case of an even string or a single character in the case of an odd string. If we get down to that, we know that we've succeeded and we can just return itself, the input string, because we always have to return something. So what is the recursive case? As I showed, you're going to need to flip the first and last character and then recurse on the substring that's excluding that first and last character. So we're going to return the string with the first and last characters swapped. So now let's take a look at the actual code. For the base case, we just need to check the length of the string. So if it's empty, that's going to be length 0. If it's a single character, that's length 1. And so here's an example of a case where you want to combine those two cases, and you want to say that if the string is less than or equal to 1, then your length is less than or equal to 1. You're going to want to just return the input string. For the recursive case, we have to build a new string with the first and last characters swapped. That's because strings are immutable. If we were working with a different data structure like a set or a list, we would have to add something and then remove something. But because they're strings, it's going to be a bit simpler. So we can return the first the input character at the end. So that's input length minus 1. At the end, we're going to put the first character, so that's input char at 0. And then in the middle here, we have to call reverse on the string in between those two. So it's going to start not at character 0, but character 1. And then remember that the last parameter is usually the character after we want. So normally that would be input.length if you wanted to get the whole string, but it's going to be input.length minus 1. So let's take a quick look at some examples. So we're going to run it on the empty string, a single character because that's kind of an edge case, and then an odd and an even number of characters. So we've got the empty string is just empty. The A came in reversed as itself. And then reading this backwards, there's H-E-L-L-O, hello, and J-O-H-N, John. So that is correct. And I just want to remind you, the things that we've learned in this one are that we can have multiple base cases together here. We're checking for less than or equal to 1. You might need to check for the first few different base cases and make sure that you get the right answer. And also with strings are easier because they're immutable. You can just build a string. But if it was anything else like a stack, really a stack is a nice thing to work with. But if you do it with a stack, you're going to have to push and then make your call and then pop, assuming that even if there's only one thing going on here, because the caller is going to depend on that stack being, it's the exact same stack. Even though you might think it's different because, oh, well, I got it as local. But it's not. It's the exact same stack as the caller and the callee are seeing. So you have to restore the stack if you are going to back out of something. This one is going to be a function that tests a string, so no building now. So this is called isPalindrome. A palindrome is a word which is spelled forward and backwards the same way. So ABBA is a palindrome, kayak is a palindrome, no is not a palindrome. By definition, an empty string or a single character is a palindrome. So of course, we're going to start off with those two basics. We want to have a base case, and we want to have a recursive case. So let's take a closer look at how this algorithm works. So again, a palindrome means that the first and the last characters are the same, and the substring in the center between those two characters is a palindrome as well. That's the recursive definition of a palindrome. And so that's the way we're gonna, that's the algorithm we're gonna use. We're going to check the first and the last characters and see if they match. If they are, then we're gonna check isPalindrome on the string in the center. That's true for the odd number of characters. For the even number of characters, we're gonna do that. For even, we're gonna be left with the null string, which we define is a palindrome. For the odd characters, after we check the inner character, the A and the A, then we're left checking the single character, Y. Single character is by definition a palindrome. So hopefully you get the idea that the base cases are these two first cases. If it's null or if it's a single character, then it is going to be a palindrome. Otherwise, we're going to have a recursive case of comparing the first and the last characters and then checking, calling recursively here. And really, that's really two separate things. So I would consider that the checking of the first and last character, I would consider that to be actually a base case checking for failure. So if the first, like here, no, first and last characters are not the same, we want to return false. Otherwise, we're going to make a recursive call. So let's take a look at that. So the base case is for success, if it's empty or a single character, we want to return true. And then the another base case for failure is if the first and last characters are not the same, then you're going to have to return false. And lastly, the recursive case, you want to recurse without the first and last characters. So you are going to have to take a substring of this and grab that substring in the middle without the first and last characters, and you're going to just return isPalindrome of that. You don't have to, as in the past example, you had to, actually not this one, but this one up here, you had to return this value plus that value. Here, we're not going to do that, but in some ways we are. So you could say that this is actually the definition of, we're returning true and the recursion of the first, the recursion of the smaller substring. But since true is always going to fall out of the logic, we don't even bother to mention it. So this one I'm actually not going to give you the code for, but you've got everything you need to write the code for it here. And so I want you to go off and do that one on your own. I've given you some examples here of palindromes that you can try. So we've done 3 problems with simple recursion, and now we're going to look at 3 problems with recursive backtracking. This problem comes from the Building Java Programs, Chapter 12, Exercise 12.18. Actually, that's 12.18 is ways to climb, but I would suggest you try 12.18. The book also covers traveling northeast in full, and I would suggest you look at that before you look at this. So what I'm going to do is the problem in the book is called traveling northeast, and they use a helper function to kind of work your way up. So in most of the recursive situations we've looked at so far with simple recursion, we had a parameter like n here, and it would get smaller and smaller and smaller, or it was a string, and the string would get smaller and smaller and smaller. And we can stop our recursion based on that. But the book shows you in traveling northeast that they use a helper function, so that there's a goal x and y, and there's also a current x and y, and we recurse upward. So we head towards those goals, and then it's no longer checking if it's 0 or empty or null. We're checking whether we've hit or exceeded the goal. I'm going to do a slightly different tack. I'm actually going to try to recurse backwards, down towards 0. In this case, towards 0, 0. Because in traveling northeast, the assumption was that we all started 0, 0, and we would travel north, up, or in the y direction, and east, or in the x direction, until we got to a certain point. So it is possible to start at that certain point. That's the xy that's being passed in here, and to recurse downward towards the 0. And so this is actually traveling southwest instead of traveling northeast. Now I still need a string result here. I technically could do it without it, but it would be very difficult for you to see what's going on. It would require some spacing issues and stuff. So I've decided I will go ahead and use this string result to build the answer so that I can show you both the successes and the failures as we go through here. So I hope you've read the book about traveling northeast, that you've watched the practice it on ways to climb, because it's going to be a similar type of algorithm. So what we're going to be, we need a couple of different base cases. So we're going to have a base case for success. So as I mentioned, we're going to be starting in the upper right somewhere. If this is the grid here, we're going to start in the upper right, and we're going to work our way down left to 0, 0. So the base case for success is we actually hit 0, 0. And but there's also a failure case. If for example, we start at 2, 2, and we're heading to 0, 0, and we just go straight south, 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 we're going to fall below 0 in the y direction. And so whenever we fall below 0 in either the x or the y direction, we need to stop. So there's a second base case for failure. And then there's a recursive case. So if we haven't failed and we haven't met our goal, we want to try going in the west direction. We want to try going in the south direction, and ideally we want to try going in the southwest direction as well. Although for simplicity, I'm not going to do the southwest direction. I'll show you what you need to do. Okay, so the base case, let's work on that. So again, if we have reached our destination, which in this case is 0, 0, we want to print out the path just to the output. The failure is if we've gone too far. That means we are below 0. We want to return and backtrack. We don't have to print anything, but we're actually going to print something just so that you can see what the failure cases are like. Because again, as I was mentioning, the real critical understanding for recursive problems is understanding what does the call tree look like? What does it look like from one recursion to the next? If you understand that, it's easy to write your recursion. And then the recursive case, we're going to explore going south, going west, and then again, kind of southwest. So let's take a look at that base case first. How do we know that we've reached our destination? Well, that's just 0, 0. We need to check both x and y. And if we have met both x and y being 0, we want to print the path out. So that base case failure, if we similar, we're going to check if either the x is less than 0 or the y is less than 0. We need to just return. We're not going to print anything, and I'll show you where we're going to return into. Okay, so here I'm going to print out failed, and that'll just be, it'll help you see what's going on. So that recursive case now, we need to explore going south, going west, going southwest. So here because the helper is so much simpler, all we have to do is just subtract 1 from either the x or the y, or in the case of southwest, both x and y. And then we're just going to stick on a letter to the result for whether we're going south, going west, or going southwest. I'm going to comment that out just because it makes the output so much more complex. So let's see what happens when we run this. So I've got it programmed in to start at 2, 2. So you can go, a success is, for example, going south, south, and west, west. That's one solution. You can go southwest, southwest. You can go south, west, west, south, or west, south, southwest. So we've got, those are the ones that, but I wanted to show you the failures so that you could understand what happens really, and where does this return to? I think a lot of students don't really understand that. So let's assume we come in here with 2, 2. It's going to skip past this, it's going to skip past this, and we're going to start our first recursion. So the first direction it's going to take is going to be south. So it's going to be called with 1, 2, and south. So we come in here, again, skip this, it's not failure, it's not success. Now it's going to come to this same one here. So now it's going to be, x will be my 0 and 2, and it'll be south, south. Then we come back in here, and again, we haven't reached it, and we haven't gone too far. Now we're going to call it with -1 and 2 and south, south, south. Finally, we're going to see some action here. So when we fall into that third call, now it says, nope, haven't hit it, but yes, we have fallen too far. So we're going to print out south, south, south failed. Okay, the thing that I think most students don't understand is what happens now. Where does that return go? It goes back not to here, but we're now going to make the second call here. So we did south, south, and now that's south here. Now it's south, south, west. So we are going to build a new string. It's only because Java strings are immutable that we don't have to remove this south. If they were mutable, or if we were using an array list, we would have to stick on the south and then remove the south. Because if we didn't, now just sticking on the west, we would end up with south, south, southwest instead of south, southwest. So we're going to do that south, southwest. So now it'll be, I think it'll be 1 and 1. We started 2, 2, and now we're at 1, 1. And south, southwest. Oh, actually it's 0, right? 2, 2. We went south, south, that's 0, and now west, now it's 1. So 0, 1, south, southwest. So we come in here, and we haven't hit the destination, we haven't gone negative, so now we're going to do south, southwest, south. That's this one here. So we're going to do south, southwest, south. So that comes in here, and that one fails. So it says that's failed. It comes back out here. Now, if we did a southwest, it would do that next, but it's not. So now it's going to return out of the south-south directions entirely. Actually, it's going to do, it's returning out of the south-south. I get confused myself. We did south-south-south. We did south-south, south, south-southwest. Oh, God, now I am confused. It's going to return out of here, though. And then it's going to come back, and then it did the 2 souths, and now we're going to test a west onto it. So it sticks a west on, and it goes back in here, and that's when we get the success, because now it'll be 0 and 0. So we get west. So this is hard to understand without drawing it on paper, and that's why I like to actually draw the diagrams that they show in the book with the call trees. And I showed that in my video for 12.18, and I would suggest you try to do that. if you can see what the call trees are, then you'll see, oh, what I need to do at each point is I need to try calling it with a south and calling it with a west. All right, so I mentioned that it's only because Java strings are immutable that we have this easy time. We don't have to pull anything off. So I wanted to show you what happens if we do it with a mutable data structure. So I have the exact same problem here, except that I've replaced the last parameter, instead of being a string, to be a list of strings. And so it's called initially with an empty list. And you can see that the base case and the recursive case are exactly the same because it doesn't deal with any of the output. So that's fine. In fact, this still works because it's a println. It takes that parameter fine. So where it's going to be different is in the recursive case. So we still have the same idea that we want to try going south and we want to try going west, and of course southwest. So what happens now is that, as I mentioned, we actually have to modify the result list. So we have to add south, and then we can try traveling there. And then we're going to add west, and we're going to go try traveling there. So let's see what happens if I try running this right now. So we're going to skip over the initial. Okay, so here's where we start the new stuff. So just like before, it's going to try, the recursion is going to go, it's going to go try going south first, and then it's going to recurse, and it's going to go try going south first, and then it's going to recurse and go south a third time, and that south a third time is going to end up with a negative. It's going to print out the result failed, and then it returns, and then it moves on to the west, and it adds the W, but you see that's where it adds the W. It did not replace the S. That's really what we want to do, is we don't want to go south and then west. We want to go south, southwest. And so that's the first bug. So in order to fix that bug, you need to actually remove the south from this. You need to get rid of this last south so that you can start adding west. So let's see what happens when I run that. And let me go down here. So here's that south, south, south we were just at. It prints the failure, it returns. We come and we remove it. And so now it's just south, south, and we add the west, so that's good. And then it recurses, and so it goes in here, and now it's going to add the south again. And that is going to, when it recurses, it's negative, so it prints a fail. South, south, west, south failed. We return from that call to south. Now it's going to try doing south, south, west, west. And that one succeeds. Then it's going to come back out of the call, and now it should be, instead of south, south, we did the south and the west, so now it should be looking at south, southwest, I think. And that's not what we end up with, because we still have that west, west in here. So the second west is still in here. We need to get rid of it, because it's in Java, this is not just some structure that gets copied each time. This is actually a pointer to that linked list. And when you modified it the first time, it's going to, it's still going to be modified when you come and look at it again. So you actually have to remove it from the second one as well, even though you think you're done, because Java, the caller still points to that same list. You need to fix that as well. So now what we should see is south. We should see these first two failures. We should see the success, but then it shouldn't have the west, west, south, south. Let's take a look at what we get. Okay, so we get the west, west, but now you see that it pulled off not only the second west, but the first west. And now it's going the southwest, south direction. So, so this is what you need to do. You need to actually pull it off of any time that you have a recursive call. You need to pull it off afterwards. You need to undo that move, regardless of whether you're quote-unquote done with this routine, because you have a caller, and that caller is still going to be looking at, when you modified result, it's not a local copy of result like it would be if it's a string or an int. It's looking at you're sharing the view of that piece of memory. Okay, so what did we learn from this? We learned that, taking a step back from the first recursive backtracking, we learned that you need to generally are going to be recursing different options, because otherwise there wouldn't really be a need to backtrack if you only had one path. So you're going to have multiple paths to explore. You need to check to see whether the path fails, and if so, you just need to get yourself out of there. Sometimes you're going to print, sometimes you're going to return. And that's actually another interesting question. What happens when you return a value? If you return a value, you need to constantly check to see what the value was that came back, and decide whether you need to return from there or not. And then we also explored what happens versus strings, which are immutable and they're pretty much easier, versus if you have a structure where it's really a pointer, and that pointer to the structure is shared between all your calls. You need to make sure that you fix up the data structure before you get back. The last problem I'm going to show you is completely new. It doesn't relate to anything in the book, but it is a recursive backtracking problem in the similar kind of style. So what is this problem? It's called find sum zero, and the idea is that if you have a group of random integers, is there a way to add and subtract these numbers and end up with zero? So in the case of these three numbers, you have to, it's actually quite exhaustive depending on the numbers, to try to figure out, well, 56, 69, those are both big numbers. 13 is negative, and you might try, okay, 69 is the biggest. If I subtract 56, what's left? Oh, it's 13. So that's actually what you can do. You can subtract 69 from 56 and 13, you'll end up with 0. On the other hand, something like 47, 25, and 71, I would look at it and say, oh, 71, that's the biggest number. What if, can I subtract both of these numbers? But that's 60, 72, so it's not quite 0. So the answer is no, you can't do that. As soon as you add another number, it becomes much more complicated. So here, figure out how can you add these numbers together. It's pretty tough. And that's why a recursive program is a really good option. So recursive program can explore all the different possibilities, and it figured out for me that if you subtracted 62, 16, and 21, that would offset the 51 and 48. And similarly here with this one here, there is no set of numbers, but looking at it, it's really difficult to figure that out. So this is one of the beauties of recursion. You can figure out things that you cannot see. So the input is a stack of, we call it remaining random positive 2-digit numbers. So in the recursion, we start out with the initial stack, and it gets smaller and smaller and smaller as we pull items off of the stack. And of course, stack, you're going to pull items off the top of the stack, but it doesn't really matter. You can access the numbers in any order. And here is the output, which is another stack, and this is the numbers that we've looked at so far. So what we're going to do is take each number one at a time. We'll keep the same order. We'll put them into the output stack one at a time. Actually, you know what? These are actually reversed. I drew these by hand, but a stack that starts with 16 at the front is going to have 16 at the bottom of the stack. But again, it doesn't really matter. So we're going to take them one at a time, and then we're going to put them into the output. And we're going to put them, try adding it positive and try adding it negative. And then once we've found a place, we're going to go to the second number, and we're going to try adding it positive and adding it negative. And each branch, we get twice as many options. So there's quite a few branches it's going to explore. So let's talk about what you're going to need to know is what is the base case. So the base case is when we're done. So there's success and failure base cases, right? Should be obvious. So what does success mean? Success means that we've picked off all the numbers from the stack. So it starts off with 3 numbers, and then there's 2 numbers, and there's 1 number. And when we have nothing left in the stack is empty. That is a base case. And that if the stack is empty and we've been called again, that's not a good sign. That means that we have not found a solution. on the other hand, you always want you need to check your base case for success first. So the base case for success is that this sum here, which grows as we throw each number into the output, when the sum reaches 0. So if we manage to hit the sum is 0, and we've consumed all of the items in here, then that is that's success. And I just realized that there's actually this edge case where if you added a subset of the numbers and hit 0, it might appear to the algorithm that it was success. So you do need to check to see if the input is empty, and if the input is empty and we've hit the sum. Okay, so if those two conditions are both met, then we're going to want to that's success. And so this is a Boolean, so you're going to want to return true. So the failure is that we've pulled everything else out. The stack is empty, but we haven't hit 0. That is failure. So if it's not one of those two cases, then we're somewhere in the middle. We still have some items in the stack that we are processing, and we've got some numbers in the output. So what is it we want to try doing? We want to take a number off of the top of the stack, and we want to try adding it to the output positive, and we want to try adding it to the output negative. So let me start writing some of that pseudocode. So if the sum is 0 and you have an empty stack, you can print the result and return true. So I didn't mention that, but yeah, we should print the result. In this case, this is an unusual recursion as well, because there may not be any way to do it. It may just fail. There may be no way to add this up, and that's a little bit different than we've had before. So, but if we do find it, we want to print the result and return true. Now, if the stack is empty and it's not a zero sum, that means it's false. We're just going to return false. You might want to print that it failed just so you can see what's going on. Otherwise, you want to try adding the number positive, and you want to try adding the number negative, or basically subtracting the number. But because we are dealing with stacks, remember from our last example, you can't just add the number to the sum. You're going to actually have to push it onto the output, try the recursion with it positive. Then you're going to have to pull it off of the output, remove. Then you're going to have to push on the negative version of it and try the sum minus that number. And then you're going to have to pull off the output again. But here's the trick that's different about this problem than the before. So we have now not only one data structure that's a pointer and therefore is affected between runs. We have two data structures. And so if you have tried the positive way and it fails, and you tried it the negative way and it fails, then you need to restore the input. So whatever you pulled off the input to add positive and add negative, you need to put that back onto the top of the stack. Because if you don't do that, then when the next execution happens, it's going to say that it's not going to see that it needs to deal with that number anymore. So you need to restore that last number as well. So it's a little bit tricky. You have to be pushing and popping, and then around all of that, you have to pop the stack, and then you have to push it back on. If at any point you return true, you want to abandon your code. You want to return, pass that return true to let it percolate up to the caller to stop the evaluation. So it's a little bit trickier. I'm not going to give you the code for that. I want you to try it on your own. You will need some test code. So I'm going to show you that test code. So here's some test code here. It takes an integer n, which will tell you how many numbers that you want to try. So you notice that some of my inputs here were 3 and some of them are 5. So that's the n here. So you're going to create a new stack. You're going to want to fill it with random numbers, 2-digit numbers. So this will give you 0 to 98 and add 1, so it becomes 1 to 99. And you want to create a new stack for the output, and then you want to call this with the that stack with all the numbers in it, the output stack, which is blank, and then 0 because you want the sum to start at 0. So you can write this code on your own, try it with that test code, and you should find be able to find some of the sets of numbers will work on you for it, and some won't, but some will. So if you can do that, I think you've pretty much mastered the levels of recursion, both simple recursion and advanced backtracking recursion. So congratulations to you.